So I had ROS1 slash ALK. They kind of go hand in hand. And my drug was, forgive me, Lorlatinib. Um, oh, that's, how do I?
I'm trying to kind of do it.
You just scroll.
The arrow.
There we go. Okay. All right. So my drug works for non-small cell lung cancer. So 80% of lung cancer diagnoses are non-small cell lung cancer. It's a very dangerous type of cancer. I think the general survival rate for the first 5 years is very low, like under 30%. With this drug, that survival rate goes up to about high 70s, which is pretty good, but there are mutations that are forming that cause this drug to be less effective due to resistance. So there are quite a few drugs on the market for non-small lung cancer. Some of them have been presented today. I think someone had tepotinib. No, there's, I can't pronounce these. So there's a lot of genes that cause non-small cell lung cancer that are easily targeted. We all did EGFR, obviously, and ROS1 is also a large one. ROS1, basically what it does is it's active in cell growth and differentiation. So it's one of the receptor tyrosine kinases that starts the RAS-RAF1 whole complex. So once it mutates, what will usually happen is ROS1, the gene will end up fusing to another gene, which activates a sort of uninhibited cell growth. So that's usually what happens in cancer cells, is it just causes an over expression of ROS1. So obviously, when this drug is ineffective due to these mutations, such as the ones that we've been working on, you need to find a new drug that works better. As also for lorlatinib, I mean, it's a good drug, but there are some side effects. There's some neurological side effects, and it can be used in children, but it's kind of still in testing as far as the neurological symptoms, such as memory loss and things like that. All right. So the goal for this experiment is to identify a drug in which the ROS1 and ALK mutants, for mine specifically L2026M and G2032R, will have little resistance, and we want to, again, preserve that healthy wild type in normal healthy cells. We don't want that to be affected by this new drug. So the research plan, we're applying computational methods. So obviously we're doing protein modeling, then docking, virtual screening using HTVS, XRSP, and identifying ultimately the properties of the ROS1 wild type, its mutants, as well as lorlatinib, and comparing those to the properties of new potential drugs. So essentially, we just want a drug that is low in potency to preserve those healthy wild type cells and high enough in potency to combat dangerous cancerous cells that are mutated. Okay, so for the computational approach, like I said, we're preparing our protein, we're doing modeling, we dock it, we're doing virtual screening using huge databases to really cut down the amount of time that it takes to find an effective drug. And then we compare the existing drug and experimentally identify drugs via their IC50 values. The computational approach is really unique because it's cost effective. You think about it, there's like billions every year put into research, and it can take decades even to get your result. It's efficient, there's a smaller margin of error because it's less human error really, and it's just such a shortened time span of research. So I'll talk more about that in this next slide. So it eliminates the trial and error research, which is like a really big component because trial and error requires so much investment for hundreds, thousands of potential proteins, and it takes these investors a really long time to see that back. So, you know, a lot of people in our field are struggling and trying to keep up and get, you know, that investment back and be able to make money for their companies. And it is kind of like a drowning fight, you know. And when you're doing trial and error, there's a low chance of success within a short time period. It really is just an issue of chance. It's probability. So when you introduce this innovative approach, you allow for possible success within such a short time frame that it could change pretty much everything for these people that struggle with cancer and chronic health issues. People wait years and even decades for treatment, and with something like cancer, if you don't get that treatment within this short period of time, obviously it can have dire effects. So we can provide cures and treatments for illnesses and medical conditions quickly, and also provide rapid progress for understanding biomedical pathways that have been worked on for years and decades that we just can't quite get the knack for it yet. So that's enough about computational. For this experiment specifically, we used virtual screening to identify 5 compounds, which I can credit to my bioinformatics student, to compare lorlatinib to a more effective drug for non-small cell lung cancer. As you can see below, there's a couple pretty good proteins that were identified that are highlighted, which would be able to preserve the wild type. You want to keep your healthy cells, but also target those mutations and become more effective. So yeah, you want your high IC50 values so that there's lower potency for the wild type cells and a low IC50 value for the mutants so that you target those with a higher potency. And that's it. Any questions? Very happy this camera can't see me.
Okay, so we have a key part is down the testing for finding the IC50. You mentioned here, but we please create a table. You have this compound 2 proteins so that the table of the 12 value. Yeah, so I think that really is more.
Yeah, there is more in my final paper. I kind of didn't realize that this was supposed to be like, oh, present everything you've done. I was just like, oh, it's like a general proposal for if you were to do computational, but there, it's in my paper, I promise.
Okay.
I get to leave now.